Okay, can everybody draw a tree? Now, the concept with this tree is they had 3 children. You need to have 3 branches. The first child, the second child, the third child. Each possibility is a boy, girl, boy, girl. So then from your sample space, this is your sample space, we can determine what's the probability of 2 boys and a girl, because the order didn't matter when they did that. Now your probabilities also come from this. 1/2, 1/2, 1/2, 1/2, 1/2. So each one of these are in fact 1/8. This is your boy, 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 and boy, whatever. 1/2 times 1/2 times 1/2. Boy, girl, boy. 1/2 times 1/2 times 1/2. And remember, all of these have to add up to 1. So you can do this in a number of ways, should we ask the probability. So in other words, if they ask the probability, what is it, they have 2 boys, you can add up all the ones that have the 2 boys. Do all the 1/8s, and then add up the 3 to get 3/8. This is the same exact setup if we flip a coin. Why is it the same exact setup to flip a coin? There's 2 outcomes. Very good. A heads and a tails versus a boy and a girl, male and female. So it's going to look exactly the same. Okay, a student must choose from 7 classes to take at 8 a.m., 4 classes to take at 9 a.m., and 3 classes to take at 10 a.m. How many ways can the student arrange the schedule? This is your counting principle. 7 times 4 times 3. 84 different ways. So when you head to college next year, most of you, you're looking at arranging your own schedules. There's a lot of different ways you can set up your schedule. The chance that then you had to just identify which ones these were: subjective, theoretical, and empirical. So the chance that corporation A stock will fall today is 75%. This is a subjective measure. Subjective because, did anybody have empirical? No? Everybody had subjective?
I was tempted, but I was tempted as well.
Okay, but Shayla, what'd you put? Right. Okay, empirical first because they do look at just this year's things, but subjective because there's really not a way to measure exactly how much your stocks will fall. They probably look at they absolutely look at all the conditions that were created by this. Like say there's somebody's money is devalued in Greece or China or somewhere across the world. That affects our stock prices. If we have something going on here in the United States, something bad happened, the oil prices dropped or whatever, or became higher, then our stock prices will change. So what they do is they look at trends and patterns, and they know that it's going to fall, but by how much, they pretty much have to have a little bit of their gut feeling in there. It's a little bit too close for them to pinpoint exactly. If they knew exactly, we would never have any problems with the stock market. Like that's another reason. You know, if everybody knew exactly what was going to happen, they would never have any issues. We would never hit bottom. We would never have crashes. We would know ahead of time, but we don't. They can only put their gut feeling into this. You know, the last time I saw this happen, Turkey lost their value of money. This happened in the United States. This happened. We dropped so far. So they're putting their gut feeling in there. The probability that a person can roll his or her tongue, is 70%. This is your experimental, your empirical. Not that it's experimental, it's just that we take it from that group of people. That's the study that you're doing. That's your empirical study. That's why they like to use empirical, not experimental. So that's your group of people that you're asking, can you roll your tongue, yes or no? 70% of them are going to say yes. The probability of rolling 2 6-sided dice and getting a sum greater than 16, greater than 9 is 1 out of 6. Okay, that's classical. That will not change. That's your theoretical. Theoretical as well as classical. You can give me either one. I lean more towards theoretical, but classical is fun. I think your book does the classical. Okay, using this chart, find the probability that a randomly selected firm will have at least 10 employees. Number of employees. Is this chart independent or dependent? Each column. Independent. If you're in this category, you cannot be in this category. So the fact that they will have 10 or more, 10 or more. So you're going to have to add these three columns up together and get your percent. Find the probability that a firm will have fewer than 20. Well, here's my fewer than 20. Now, you had a choice. Here's my fewer than 20. No, you didn't have a choice on this. Okay, so you have to add these up together. Good? That's because these are independent. Independent, in other words, they are mutually exclusive. If you're in one category, you can't be in another category. Okay. Again, this uses your chart again. Find a probability that a student failed given. Remember, we have to do the given first. Given that the student took the exam for the first time. So put your circle around for the first time. Do the given first. The probability that they failed the exam, you're going to stay right in that row. So 2,058 over 6485. 3 decimals. Yes, sir.
How can we use 2003 over 3,900?
Because this is what you have to concentrate on first, this given. This given says, I want to know, given, this is a dependency problem. Given that the students took the exam for the first time, that's the group I want to look at. So I only want to look at this group. I can't go out of there. So now I'm going to use this total. Now, you can see your dependency because if you say the probability that a student failed, whether it was a repeat or anything else, the probability that a student failed alone is what? 3903 out of what? Is that the same as this one? No, so there's a dependency. Whoa, there's a dependency here.
Whenever it says given, you automatically know.
The given has to go first. The given is first. Like this one. Given that the student passed, you got to look within this first. And don't come out of that circle. Given that the student passed. So we want to know the probability that the student repeated the exam. I can't come out of there. 407 over 4834. Good? Okay. This is always a cute one with the socks. Your sock drawer has 18 folded pairs of socks with 8 pairs of white, 6 pairs of black, and 4 pairs of blue. Lay them out. Know how many total you have. What is the probability, without looking in the drawer, that you first select and remove a black pair, and then select either a blue or a white? Now, when you remove, is this an independent or dependent? Dependent. This is without replacement. That means you keep it. That means your totals change. This is a dependent event. So the probability that you get a black, and lay this out. Black, not black. Okay. So the probability that you get, oops, a black or a blue or white, right? Yeah. A black or a blue or white, right? Not black. They could have just said not black. Okay, so a black is 6 out of 18. You take that pair, you're holding it. Now you have 17 left to choose from. Blue and white together, adds up to 12 because we didn't touch those yet. And this is an and situation. I want black and a blue or white. So I'm multiplying these guys. Multiply them, reduce them to lowest terms, or give me 3 decimals. And we want to know, is this unusual? No, it's not. And again, it reverts back to your normal curve. Your normal curve, remember, for the plus and minus is at the back. So they use a standard 5%. If it's less than 5%, we're going to consider it unusual. It's actually half of 5%, but we're going to use of their 5% mark. So this was not less than 5%. It's 23.5% probability. Are we good on that? Okay. A random sample of 250 working adults found that 74% of them access the internet at work, internet at work, internet at home. 74% access the internet at work, 88% of them access the internet at home. And 72% of those that do access this, access it at both. There's your both. Now, if these were just an or where you're going to add them up, 74 plus 88, isn't that greater than 100? You can't have greater than 100%. So it shows you have to subtract the overlap. This is where they overlap. Think of a Venn diagram. This is where the both is. So you've counted it in the home and you counted it in the internet. So you have to subtract it out. And yeah, the first percent is high. Think about your own situations. Granted, you're not at work, but you pretty much all have access to internet at home. You know, 10 years ago, my old book, 15 years ago, when it was written and it came out, these percentages were really, really small because a lot of people didn't have internet both at home and at work. No, but now it's everywhere. It's in half the businesses you go into, coffee shops, everywhere. You have it here at school. Think of it at school and at home. A card is selected at random from a standard deck of 52 playing cards. Find the probability that the card is between 4 and 8 inclusive or is a club. So I want the probability, and let's get used to writing the statement. Between 4 and 8 inclusive or a club. Inclusive means you're going to count those numbers. If I normally say between 4 and 8, these guys are between 4 and 8. But inclusive means count your end numbers. It's kind of like the hard bracket versus the soft bracket, right? In an interval notation. Yes? Yes. Kind of like your hard bracket means include them. Your soft bracket means don't include them. So now, on this or condition, we're going to add them. However, there are 4, 5, 6, 7, 8 of clubs. So I counted them here, and I counted them again in my clubs. So I have to subtract the overlap. So the 5 cards that I counted up front as a club also, I have to subtract.
So between 4 and 8, you're including 4 and 8?
Including because of this word inclusive.
Okay.
Yeah. If it didn't say inclusive, then I'm only counting 5, 6, and 7. It's kind of like your interval notation, Julia. Like if you use a hard bracket, you're counting it. If you use a soft bracket, then you didn't count it. Yes?
For the club, that's like the clover.
The clover.
Are there other cards that are base cards that have clubs?
There are 13, there are 4 suits. Every suit has 13 cards in it. So every suit has, we consider ace as 1 through 10, then a jack, a queen, and a king. So every club has 10, 13. Every spade has the same exact cards, but a little, I don't know, looks like a shovel thing. I guess that's where they get the spade, I don't know. A heart, 13. 13 of them have the little hearts on them. And then a diamond. And it's kind of nice because these are separated into black and red. So altogether you have 52 cards. When you use cards and you're asking for a specific card and then a specific category, you're going to have an overlap. Because if you're counting up all your diamonds plus all your face cards, you had 3 face cards that were diamonds in here, and you're going to count them twice. So you're always going to have to take out your overlap.
So probability the first category, and then probability the second minus the overlap.
Minus the overlap. Now, sometimes they're independent. The probability of a 4 or 8 of any card, I'm not going to find an overlap. I have how many 4s in my whole deck? 4. How many 8s in my whole deck? 4. And we're just going to add these guys. There's no overlap in that because they're independent of each other. The overlap is when you pick like a suit or an even or something. I don't think you pick an even in cards, but some kind of suit usually. Usually the suit and the cards. Questions? Feel free to stop me and ask a question. This is important. A card is randomly selected from a card deck of 52 playing cards. Find the probability that the card is a red or a queen. Now here's a perfect example. How many red cards in your deck? It's half of your deck, right? So I could put 1/2. I could put 1/2. It's probably easiest to keep the same denominator, just because you like to see what you're looking at. How many queens in your deck? 4. This is why I usually like to keep the same denominator. You can absolutely do that on your calculator if you like. Now, you ask yourself this: how many red queens? 2. So I counted them in my reds, and they were my queen of hearts and my queen of diamonds. And I counted them in my queens. So I have to take out my overlap. Now, if you want to do it like this and put it into your calculator, you're going to get the same answer. But I think that's why I like to keep them the same denominator. It's much easier to actually see this. Good? And do it in your calculator. Give me 3 decimals. 3 decimals. You can give me percents if you want to. You can just move this and give me a percent. If I just ask you the probability, I'd leave the 3 decimals. If I ask you what percentage, then go with the percent. The probability, you could just leave me in decimals right now, because we're not doing anything else with them. Okay. This enters your permutations and combinations. Remember, permutations have no order. Permutation order matters. It matters what order we line things up in. It matters what order something comes first, who becomes president, who becomes secretary. So 15 cyclists enter a race. How many ways can they finish first, second, or third? If you struggle with the permutation, lay out your 3 places. You have 15 to choose from, then 14, then 13, and your counting principle says multiply. When we ask how many ways, you're going to get the big number. If we ask what is the probability that the exact people finish first, second, and third, then that would be 1 out of this. Probability is always between 0 and 1. So watch the difference between how many ways and what is the probability. And again, you can write it as a permutation, 15p3. It's probably easiest. 15 things, 3 at a time. 5 players on a basketball team must choose a player on the opposing team to defend, 1-on-1. How many ways can they choose their defensive assignments? Start with your 5 people. The first person has how many people to pick from? 5. Then the next person has 4. Then the next person, and that last person says, don't leave me stuck with him. He's like 3 feet taller than me. So that's where this permutations come in. This is called factorial. If you're going to use them all to get all the way down, 5 factorial. How do I write this as a permutation? 5p5. Good. Everybody okay with the permutations? Yes. Order matters. 45, yes, because we want to know when did they finish first, second, and third. 46. Order, in this case, we really want to consider like the order matters. An employer must hire 2 people from a list of 13 applicants. How many ways can the employer choose to hire 2 people? So you say to yourself, does it matter what order I hire them? If I need to hire 2 people from 13 people, does it matter what order I hire them? I just need to get 2. So therefore, it's going to be combinations. Order does not matter. So I want 13C2. 78 ways to hire 2 people, 2 groups of people from my 13 applicants. So when you go for a job, you really need to stand out if there's that many ways to pick applicants. Now this one's a good one. A security code consists of 3 letters followed by 1 digit. Start like this and leave your lines. Then look at the details. The first letter cannot be A, B, or C. So out of the 26 letters, I take out A, B, and C. I have 23 to choose from. And no other restrictions here. So I can repeat. So I come here, I have all 26, I have all 26, and I have 10 digits, 0 through 9. Don't forget the 0. And the counting principle says multiply these. I have 1,055, 480 ways that I can make this security code. What is the probability that I get the correct code? There's only one correct code that's going to work this keypad or whatever it happens to be, right? That's your 1 out of this. There's your probability. Everybody okay with that? You've got a lot of choices because you've got a lot of letters.
Do you have to put the decimal, or can you just leave it as a fraction?
Oh, you can leave it as a fraction. You can leave it. If you leave in your fractions, leave them to me reduced fractions. In this case, this one really doesn't go anywhere. But did everybody see the difference between the ways and the probability? Yes. You get a different answer? What do you get?
Actually, with the where it says E -6 on the calculator, is that putting a lot of zeros in front of it? Yeah.
Yep. Because your probability can never be this, right? Couldn't be greater than 1. So this E is actually your scientific notation number. This is actually written as a scientific notation number. If it's a negative, go towards the negatives. It's going to get a very small number. Move this 5, 6 places. You're going to add 5 zeros if you move it 6 places. If it has a lot of zeros, it automatically goes to scientific notation. Now here comes your favorite part, your defective parts. I would pay attention to this.
It is a toughie.
Yes. It's a toughie that you might see.
Oh.
Oh. Okay. I have 200 calculators. Can I tell the difference between one calculator to the other?
No.
No. And remember, even though I have 200 people, I'm really one person is the same as the other. Even though they look differently, one person is the same as the other. So the calculators have the same kind of setup. I have 3 defective calculators. Start like this. 3 defective. They have to add up to 200. How many non-defective calculators do I have?
137.
We say non-defective, or in other words, these are good. These are good working calculators. Okay? Find, and the first part will be how many ways can I choose any three? This is your generic number. This is going to go on the bottom in the denominator of all your probabilities. So any three out of 200, I have this many ways, quite a lot of ways to choose them. My calculators will be numbered, so I'm going to choose number 1, number 53, number 1, number 27. I'm going to go like that. Find the probability that there will be no defective calculators. I need this bottom number that came from up here. How many non-defective calculators do I have to choose from? 197. How many of them do I want? 3. I'm always going to choose 3. I'm going to choose 3. Okay? So therefore, that's got to be a good size probability, doesn't it? If you think about it, if you have 200 calculators and only 3 are defective, you have a very good chance of choosing a set of 3 in which one is not defective, right? If I only had 25 calculators and I had to choose 3, would my probability be greater or smaller than this? Smaller, because I have less to choose from, right? My ratio of good to bad would be a lot bigger, wouldn't it? That's good. Okay, find the probability that all calculators are defective. How many defective ones do you have to choose from? 3. So over your bottom number, again, scientific notation number, it's a very small. It's a very unlikely chance, very small. It's not a 0 because it can happen. That if I have this great big bin of 200 calculators and I say, what's the probability that the 3 you pick out are defective? Out of 200 calculators, you say, I'll never get the 3 that are defective. And you just happen to pull out the 3 that are defective. This was the probability that that would happen. It is way, way, way less than 1%, way less than 1. But we can't say 0. 0 is the impossible. It will never happen. It's a very small possibility that you could pick the 3. Okay, find the probability that you get at least 1 defective. At least means I want 1 defective, or 2 defective, or 3 defective. So if I wanted to, I could do the one with 1 defective, do 2, do 3, and add them up. The only case I do not have is all defective. So I can do my complement case. And usually that's how they set this up. So that you found your probability of all defective. At least 1 defective. 1 defective or 2 defective or 3 defective. The only thing I don't want is no defectives. I hate the non-word. I just wish they would use good or working. So I want to come back to this guy here. Usually they set this up so that you're going to do one of them. Okay. Find the probability that you get at least 1 non-defective. Okay, 1 non-defective, or 2 non-defective, or 3 non-defective. Your non-defectives are your good ones, right? So the probability that you get at least 1 good one out of all 3 has to be a really, really high number, doesn't it? That's when you're going to subtract this guy from here. Use that complement case. Yes?
The complement is basically the opposite of unit.
Yes, it's what's left over. Yeah, it's this or 1 minus this. Yeah. Now, when they give a non-defective and a defective, you might want to go through, change your non-defective words to good, because it's always hard to deal with a not situation or a non-situation. Okay. All right, so here's another little problem. I have a group of people, a group of students. In that group of students, I have 10 seniors and 4 juniors. What is the probability from this group of seniors and juniors that I pick I want to choose 4 people to make a committee for, I don't know, whatever, some environmental thing, let's say. So I want to choose 4 people from this group to go plant some flowers outside. I want to choose 2 juniors, 2 seniors. Find me the probability that from this group of 4, I choose 2 seniors, 2 juniors. So, denominator. Nick, what do you have in your denominator? 14C4. Out of the 14, I want any 4. This is my general one, my generic, if you will. Mercedes, what do you have for your numerator? 14C2. How many juniors do you have to choose from? Go like this. I want 2 juniors, 2 seniors. How many juniors do you have to choose from? 10. And how many, you have 4 juniors to choose from. How many juniors do I want? 2. You have how many seniors to choose from? How many seniors do I want? And what am I going to do with these 2? Multiply. So John, what'd you get as your final answer?
I get one.
You didn't get it?
No.
Will, what'd you get?
I did that. I didn't get it.
27. Oh, 0. Okay. Everybody see what we're doing here? So what is the probability that I picked 4 juniors? How would I set up the probability that I picked 4 juniors? Which one's going to be the same? Denominator. Again, any 4. What's going to go in my numerator? 4C4, which is what? 1. Okay. Say I wanted all seniors. What's my denominator? What's my numerator? 10C4. Are we getting this? Okay. Vaguely. Okay, study from this, guys. Tomorrow's the test.